Hi everybody, this is George Huddy. I am recording audio lectures now for RADT 121. As you can probably tell, I don't have the world's best microphone, so you may need to turn the YouTube captions on, and I might break this into multiple videos just to make it a little bit more digestible. We're going to take a look at chapter 12 today, subject contrast. We have talked about subject contrast previously as information in the remnant beam, and your book defines subject contrast as a ratio of differential absorption. So radiation being absorbed different rates depending on what type of tissue it's going through. And please note that differential absorption is sort of a catch-all term that includes all of the interactions we have discussed previously. Specifically for general radiography, that means photoelectric effect, Compton scatter, and coherent scatter. All of these interactions represent beam attenuation, which is kind of our term for a reduction in quantity of the X-ray beam. So I've got a little chart here of what can happen to your X-ray as it passes through an object, in our case, a patient. So starting off, you've got your X-ray can do one of two things. It can be transmitted through the anatomy, aka penetration, or attenuation can happen. So please note that transmission itself is not an interaction. In fact, it's the opposite of interaction. You have an X-ray that is passing straight through your patient and hitting the image receptor, leaving a dark spot on that image. Attenuation, we've got interactions happening. So it's either going to transmit or attenuate. And if it's going to attenuate, it's either going to be absorbed, that's the photoelectric effect, or it's going to scatter. And under scatter, for our purposes, we've got two different types of scatter. We have Compton scatter and coherent. Remember that coherent produces very low energy X-rays in a different direction. They're not going to affect your image, they're just going to affect the patient dose. Compton scatter produces X-rays with less energy than they started, going in a new direction. And they have enough energy, in a lot of cases, to exit your patient and hit the image receptor. They can affect your dose if they hit you, but if they hit the image receptor, they're definitely going to have an effect on the image quality. We'll get into exactly how in a little bit. So subject contrast, it's a ratio between the X-rays that are attenuated and the X-rays that are transmitted. And your book has a couple of illustrations on this, on figures 12.1 and 12.2. You'll note that I am not using a video editor on this, so you're stuck with all of my ums and ands and any kind of verbal flubs, and I will try and correct things as I go. So figures 12.1 and 12.2, that's on pages 198 and 199 of the book. Now these are hypothetical. They're just talking about, hey, for this part that we're X-raying, we're only dealing with 100 X-rays. In reality, we're dealing with millions and millions of photons per square inch. And we're looking at contrast, which is about the differences between things that are next to each other. So image contrast, we talked about a difference in brightness between two adjacent parts on your picture. Now, subject contrast is also involved in differences. So figure 12.1 has your x-rays going through soft tissue and bone side by side. And in this example, we've got 100 x-rays going through soft tissue and 100 x-rays going through bone. Over on the soft tissue side, we have 1/2 of them, 50 of those x-rays being photoelectrically absorbed. Another 10 x-rays go through Compton scatter. What's left over is 40 x-rays. Those 40 x-rays transmit, they penetrate through. Everything has to add up to 100 in this example. So 6 out of 10 are being attenuated. Doesn't matter for our purposes of this example if they are absorbed or scattered. They are attenuated. So the soft tissue is attenuating 60%. Over on the bone side of things, of the 100 x-rays going through the bone, 70 of them are absorbed, 20 of them are scattered. Only 10 of the original 100 penetrate through that bone. So 90% of the x-rays have been attenuated in the bone. Now we're going to come up with a subject contrast for these two tissues. We're going to compare them. Look at what has been attenuated. 90% through bone versus 60% through soft tissue. You just divide them. That's how you get a ratio. 90 divided by 60 gives you a subject contrast of 1.5. That's telling you that the bone is absorbing and scattering more than the soft tissue is. So what does that 1.5 indicate? Well, it means the bone is absorbing 50% more radiation than the soft tissue, which makes sense based on what we know about how our x-rays look. So next up, figure 12.2. Now we have the same patient, but there is a disease process going on. And we've changed the density of the soft tissue, in this example, by 30%. So think of someone with arthritis. You've got inflammation and degenerative changes in the joint space, not necessarily just the bone, but the soft tissue getting denser. And now we're going to send 100 x-rays through that denser soft tissue and 100 x-rays through the bone. In this example, the bone hasn't changed. It's still absorbing 70 photons, scattering 20, and 10 are penetrating. But the soft tissue, the attenuation has changed because of the density. So now, instead of 50 photoelectric interactions, we've got 67, an increase, 30%. We've increased Compton scatter 30%. That brings us to 13. So you add those all together, and you end up with 80 photons attenuation versus 20 penetrating. So now, because we've changed the density of the soft tissue, it's a little closer in composition to the bone. It's absorbing more, scattering a little bit more, which means there's fewer photons left over to just pass through without interacting. So now we look at our contrast ratio for this example, and we've got 90 divided by 80 for a subject contrast of 1.13. So the bone at this point in figure 12.2 is absorbing only 13% more radiation than that thicker soft tissue. There's less difference between the two tissue types. much less subject contrast. All right, now that we have talked about attenuation, we need to talk about what causes it to happen. There are 3 factors that go into determining a particular tissue's attenuation in terms of subject contrast. They are the thickness of the tissue, the density of that tissue, and the overall atomic number of that tissue. Thickness is up first. Attenuation is going to increase exponentially as an area of tissue gets thicker. Now, your book has 4 centimeters. Other textbook I've seen, including this illustration, use 5 centimeters. The rule of thumb is that for every 4 or 5 centimeters, which is about 1.5 to 2 inches, every 4 or 5 centimeters of additional thickness, your beam attenuation doubles. So this illustration starts off with another theoretical 100 x-rays. This little square of tissue. No matter what the tissue is, whether it's bone or soft tissue, fluid, etc., we're just talking about the thickness of it. For every additional 4 or 5 centimeters of tissue, that cuts your x-ray quantity in half. We start off with 50, 5 centimeters down, we're left with, we started with 100. 5 centimeters down, we cut it in half to 50. We go another 5 centimeters down, you're left with half of that, which is 25. How does this affect your image? Well, let's think about an exam that we might do from time to time, a humerus. Your average patient's shoulder, typically thicker than their elbow. So the proximal humerus, where the shoulder is going to attenuate many more x-rays than the distal humerus based on thickness alone. And a lot of times our computer processing is going to clean this up. But if you look at the raw image, just what the image receptor receives, your shoulder is probably going to be brighter than the elbow. In fact, the elbow, unprocessed, may be very dark. That distal end is just not as thick. So it's not going to attenuate as much. You're going to get more hits on your image receptor on the distal end. So your textbook has an example for part thickness. Kind of going back to figures 12.1 and 12.2 in terms of the ratio of subject contrast. So we've got 2 body parts, part A, part B. Body part A attenuates 40% of the beam, which means 60% gets through, but we're just talking about attenuation to determine our subject contrast. So part A attenuates 40% of the beam. Part B attenuates 10%. Subject contrast, you just divide them, you get 40 divided by 10 for 4.0. So part A is absorbing or scattering 4 times as many photons as part B. That's going to give you a big difference in image contrast. Because part A is just absorbing so much more X-rays. So it's going to be brighter in your picture than part B. So that's the first part of our example. Now we're going to throw tissue thickness in the mix. We're going to make part B just 4 centimeters thicker. Just 4 centimeters, not even 2 inches thicker. So part B's attenuation doubles. It goes from 10% to 20%. Now, it's absorbing double the amount of X-rays. So if you run your subject contrast ratio, 40 divided by 20, you get a subject contrast of 2. So your subject contrast has decreased because part B now attenuates more X-rays, just from thickness. That means on your image, the shade of gray that part B produces is closer to what part A produces. The distinction between them has decreased as far as the IR is concerned. Both of them are absorbing more from the IR's perspective. Here's another illustration of tissue thickness and how it affects transmission. So in illustration A, you've got a thinner part transmitting more radiation. Part illustration B, you've got photons being absorbed, fewer of them transmitting. So more attenuation is happening on B because it's a thicker part. Next up, tissue density. Tissue density, think back to your basic science class in terms of how dense something is. It's a measure of how much matter is concentrated into a given volume. So it's all about how many atoms and molecules we can pack into whatever we're X-raying. It's a concentration of stuff. And unlike thickness, tissue density has a directly proportional effect on attenuation. So it's 1-to-1. If you have tissue that's twice as dense, it's going to have twice the odds of attenuating X-rays rather than transmitting them. Tissue that's half as dense will have half the chance of absorption and scattering. Because of that, you would need pretty big changes in tissue density to have a big effect on your subject contrast. Most of the time, it's the other factors. Tissue density, not as huge an effect in terms of the physical concentration of atoms in tissue. But there are cases in the body where you do have very big changes in tissue density. The prime example is a chest X-ray. You have air in the lungs. You have your mediastinum, the heart and great vessels. Those tissues are much more dense than the air in the lungs. They're going to absorb about 1,000 times the X-rays. Now, your book helpfully points out that when you just look at the atomic number of air, it's about 7.6. Soft tissue, it's 7.4. They're nearly equal in atomic number in terms of the stuff that makes them up. The atmosphere, the water, and the physical tissue in your body. Not too far apart in terms of atomic number, but in terms of density, huge. Air is a gas, has a very low density compared to soft tissue. Soft tissue density pretty close to that of liquid water. So your soft tissue is going to absorb about 1,000 times more X-rays than your lungs. So we see that subject contrast relayed in the remnant beam. So your chest X-ray has a huge subject contrast built in before you're even doing anything with your KVP, just based on the tissue density. And you do need to know to be able to rank and order these type of body tissues from the most dense to the least dense. Bone being the densest, soft tissue, musculature, glands, connective tissue, followed by fat. Fat is less dense than soft tissue and muscle, so you see a difference in the fat surrounding tissue. And then air being the least dense. Metal, like surgical hardware or artifacts, is denser than bone, so it will show up brighter. But in general, metal is not a natural tissue found in the body. It's always something that's placed there or overlaid. So tissue density. And your book has a good example of this in terms of how fat is less dense than muscle. It talks about how when you take your KUB and you can see the subtle outline of the kidneys in the abdomen, that what you're actually seeing is the fat capsule around the kidney that makes it visible, makes them stand out compared to the abdominal muscles. Otherwise, if the kidneys did not have that fatty layer around them, you wouldn't see the kidneys on the KUB. It's just a change in the density that really matters. Okay, last factor in tissue attenuation is atomic number. We talked about this in chapter 11. Your Z number, which refers to the number of protons in an element, an atom, and also the number of electrons for that element. How does this relate to attenuation? Well, as your atomic number increases, as you got more protons on an atom, it has more electrons. Or essentially, having a higher concentration of electrons, the higher the atomic number. There's more electrons around. X-rays at our diagnostic energy levels love to interact with electrons. So, if you have an atom with a lot of electrons, it's more targets, it's more chances to interact as millions and millions of X-rays fly through. You can still have interactions with, say, a hydrogen atom, which is one proton and one electron. But the odds that a photon is going to hit that one electron versus in bone, when you've got a lot more electron targets, more likely to have an interaction the more electrons you have as a target. But tissues in the body are not made up of a single element. We are composite beings. And a lot of chemical compounds are made up of molecules, so that's combos of elements. So we have an average atomic number, average Z number for our bodily tissues. Bone, it's about 20. Calcium, all the other minerals involved in bone, gives you an average atomic number of about 20. Soft tissue is mostly water, so that has an atomic number of 7.4. Compare that to our big contrast agents, iodine and barium. Iodine has an atomic number of 53. Barium has an atomic number of 56. So we already know, just without even getting into it, that you have a lot more attenuation in bone than in soft tissue. We can just look at these atomic numbers and get a sense of how much more X-rays like to play around with bone versus soft tissue for attenuation. 20 versus 7.4. But contrast agents, it's even more inviting. You can attenuate and absorb even more. That's because atomic number has an exponential effect on attenuation. In fact, if you take the atomic number and you cube it, which is multiplying it by itself to the power of 3, that's the effect that atomic number has on attenuation. Example of this, we have our average atomic number of 20 for bone. So 20 cubed, 20 times 20 times 20 is 8,000. Soft tissue, atomic number average of 7.4, we cube that, we get 405. So if you make a ratio of that, it tells you bone attenuates nearly 20 times the amount of X-rays as soft tissue. That's just based on atomic number, which is huge. We add in the other factors and it just compounds it. So bone is also more physically dense than soft tissue. So that's another directly proportional, not exponential, directly proportional increase in attenuation. And then if the tissue is thicker, that's also exponential. Okay, we're going to switch gears from our attenuation factors, and we're going to talk about scatter, what that does to subject contrast. Rule of thumb, I'm sure you've heard it before by now, scatter degrades contrast. We're talking image contrast. We got a lot of scatter. Everything looks fogged, grayed over, not as distinct from one type of tissue to the next. A good example of this is if you have tried to do a cross-table lateral hip without a grid. Going through a very thick part, the thigh, often at an angle through the tissue, so it goes through more of it. Thick part, fairly open field, you're going to have a lot of scatter in that thigh and femur hitting the plate placed behind the leg. If you don't use a grid, you're going to get a big gray mess. And you should still be able to make out the bone and the soft tissue. But the scatter can degrade the contrast to such a degree that the radiologist cannot clearly see if there's a fracture or not. Same thing applies to a swimmer's projection. If you are doing a trauma C-spine, you need a good swimmers to see all the way to T1 so they can get your patient out of a hard collar. But if you're not collimating or using a grid, you get so much scatter that the radiologist cannot clearly see that C7 T1 interchange because the scatter has degraded the contrast. Now we have grids, and we'll later in the semester get into how those work. But going back to scatter here, yes, scatter degrades contrast on your image. But now we can actually say that scatter is reducing the subject contrast in the remnant beam. You need to remember that scatter is this uniform fog bank. The entire thing, it's all random strikes from x-rays, scatter x-rays, leaving the patient, hitting the plate. Very random, but there's so many of them that even though it's random, the entire field has this uniform fog. From the IR's perspective, it means everything being imaged, whether that attenuated a little x-ray, like the air around the part you're imaging, or a lot of x-rays, like the bone, everything gets a little bit more exposure because of that scatter. Those are extra strikes against your IR. Your detector just registers more x-ray hits. So, shades of gray start looking a little bit more like each other. Shades of gray become more uniform because there's this extra signal in the remnant beam from scatter. That's noise. It's just degrading your contrast. This book has a great example of this, figure 12.3, page 201. Diagram showing how subject contrast is lost in the remnant beam by scattered x-rays randomly crossing over image boundaries and laying down a blanket of fog across the entire area of the image receptor. Yeah, it looks like we're x-raying an olive or a couple eyeballs here. But if you look on the left-hand side, you've got x-rays being transmitted, and the denser part in the middle is absorbing. So we have a blank spot where that denser anatomy is on your image. That's without scatter, but we know scatter is going to happen. You're going to have photoelectric absorption, and you're going to have scatter. So the right-hand image is what actually happens when we take an x-ray. Denser anatomy in the center is still absorbing more, and you're still getting a fair amount of transmission. But along with that signal, all kinds of scatter strikes that are going to fog up your image. So it is eating away at the subject contrast in your remnant beam. The pure ratio of what was attenuated versus what was transmitted has been degraded by the additional strikes caused by the Compton scatter. So everything is a little closer in shade to its neighbor because everything is just getting more exposure from this fog.